So as we continue working with parallel lines, perpendicular lines, we are going to construct parallel and perpendicular lines. We'll identify parallel, perpendicular, and skew lines from 3D figures. We also solve problems involving the distance from a point on a perpendicular bisector to both endpoints of a line segment, and do some examples here in a minute. But just remembering that when we talk about our parallel lines are lines that do not cross, they never intersect. Perpendicular lines are lines that will intersect at a 90-degree angle. The slope is going to, remember that, let's see here, slope is often referred to as m is slope, and it is y2 minus y1 over x2 minus x1. It's also referred to as the change in y over the change in x, okay? A reciprocal, we need to remember that a reciprocal is a number that when multiplied by another given number results in the number 1. So an example of a reciprocal might be, well, I have the value of 7, or that is known as 7 over 1. A reciprocal would be 1 over 7, because when I multiply those two together, I get 7 over 7, or 1. So there you go, that's an example of a reciprocal. And then we could even do that reciprocal with a variable. If I have a variable m, that is also the same thing as m over 1. So the reciprocal of m over 1 would be 1 over m, which is going to result in m over m, or the value of 1 again. So again, just showing you some examples of reciprocals there. Rotation, we'll talk about rotation, but it's on a plane given a transformation which each point on a figure is turned through a given angle and direction around a given point. That point's going to be your center of gravity, and then of course the distance between that point and the center of gravity will remain the same. So it's a rigid transformation, and we have been working with that for the last several weeks. Skew. Now, skew is going to be a line that is neither parallel nor perpendicular. And that's what this example down here is meant to show, that we know that it says tell whether the lines appear parallel, perpendicular, or skew. So parallel lines have the same, they will never intersect, so they end up having the same slope. So, let's see here, AB and CD. Line AB and line CD appear to be parallel. So appear to be parallel, so using the parallel. EF, let's see here, EF and EF and FH appear to intersect at a 90 degrees, so they are going to be perpendicular. And then we are going to have AB and CG. Okay, those lines are neither parallel nor perpendicular, so that's where they fall into being skew. Okay, so just using some vocabulary there. As we begin to talk about parallel and perpendicular lines, we are going to want to be able to construct parallel and perpendicular lines, to identify parallel, perpendicular, and skew lines from 3D figures, and solve problems involving the distance from a point on a perpendicular bisector to both endpoints of a line segment. Now, really, we're going to just work with some of this stuff, and it'll come to light and seem a little bit more clear, but just remember our definitions, right? So as we deal with parallel lines, they're lines that lie on the same plane but do not intersect, so they're coplanar. Our skew lines are going to be non-coplanar lines, and they do not intersect. And perpendicular lines, of course, will intersect and form a right or 90-degree angle. And our perpendicular bisector is a line array or a line segment that intersects a segment and is perpendicular to the segment at its midpoint. So remember, bisector, midpoint, we're cutting something in half, and we'll go from there. As we identify parallel lines, remember our parallel lines will be indicated using some form of symbol, and they are coplanar and they do not intersect, and that's what that means. And later on we'll talk about their slopes, but for now just knowing that they do not intersect. And our perpendicular lines are going to intersect at a 90-degree angle, and that of course would be indicated by that little rectangle there, or that little square. And these are coplanar lines that intersect at that right or 90-degree angle. And please, and you don't want to make the distinction between this. Example A, example B. In example A, this is a right angle and they intersect at perpendicular. This, in example B, is not a right angle and they do not intersect at 90 degrees because it does not have a right angle marker in it. So we do not assume. You can tell everything, just like these two lines are parallel because they have the markings for parallel lines. So we never assume. And of course let's see, talking about the shortest distance theorem as we talk about these perpendicular. All right, so as we continue talking about these parallel and perpendicular lines, I want to talk about the shortest distance theorem. And what that is it says from a given line to a point not on that line is the length of the segment perpendicular to the line through that point. Gosh, that's a bunch of stuff to say, isn't it? So I have this line and I have a point that is not on that line, and what they're telling me here is that the shortest distance theorem says that the shortest distance from that point to my line is going to be a perpendicular line. So point C, the shortest distance from point C to line AB was going to be a perpendicular line, and we'll call it at point D. That is my shortest distance theorem. Now, when it comes to a parallel postulate, it's sort of similar in a sense that we're talking about a point, and we're talking about, how about we change color up some, and we're talking about a line. And what they're telling me is the parallel postulate, let me just go ahead and write that out. The parallel postulate says that there is going to be, or there exists exactly one line in the same plane that passes through that given point and is parallel to the given line. So there's going to be one line that will be parallel to this line through that given point, and then any other line that passes through that point will not be parallel to the given line because we can only have one with the exact slope that would match with the given line that already exists. And let's see, if we talk about skew lines. Skew lines are lines that are not coplanar. Pretend those are two different planes, and they do not intersect, and they are not parallel. Okay? So skew lines are non-coplanar and do not intersect. And looking at a diagram, looking at this diagram, we need to tell whether the lines appear to be parallel, perpendicular, or askew. And I can look at these and I can say, well, line AB and CD. Here I have line AB, and line CD. They appear to be parallel. So they appear to be parallel. We don't know exactly because there's no markings on here, but they appear. Then we have line EF, which looks to be parallel to the other two lines that we just identified, but they're saying to FH, and that one appears to be perpendicular. So that one's going to be perpendicular. And then AB again, here is AB, and CG over here. They appear to be neither parallel nor coplanar, so those are going to be skew. And these are just some of the lines that they've identified here, but we could turn around and we could say, looks like DH is parallel to BF, which is parallel to AE, and is parallel to CG. You know, there are many different ways to look at this and pick out those items. but that's dealing with our skew, parallel, and perpendicular lines. Now, we want to talk about the perpendicular bisector theorem. In the perpendicular bisector theorem, it states that if the points on a perpendicular bisector, okay, so if I have a perpendicular bisector, so that means we have, say, segment AB, and it is being bisected by segment GH, okay? And if it's a perpendicular bisector, they're telling me that that's 90 degrees. And it is bisecting at the midpoint, okay? They're telling me this midpoint right here must be point C. And if that's the midpoint, then I know that this segment is equal to this segment, because that's what a bisector does at the midpoint. The midpoint means it is cut in half. And they're telling me that in this case, if it's a perpendicular bisector, then point G is equidistant to A and G, and equidistant to A and B. So if I were to draw a line here from GA to GB, those would be congruent. They're equidistant. And the same goes for a segment from AH to an HB. Those are also going to be congruent or equal, just as part of this perpendicular bisector theorem. Remember that we had said that the shortest distance from this point to a line is going to be perpendicular, and then that point would be equidistant to the segment if we formed a midpoint. But now, conversely, if I tell you that if a point is equidistant from the endpoints of a segment, so talking the converse of the perpendicular bisector theorem, what it tells me is that if I have a segment, and we'll call this GH, and it is bisected by a line, and we'll call it EF, and E is equidistant from G and H, its endpoints, then that is a perpendicular bisector. So if E is equidistant from the endpoints, then that is going to be a perpendicular bisector. And of course, F then turns out that it is going to be equidistant, and it would be a perpendicular bisector. So that is using the perpendicular bisector theorem. And let's see here, if we look at these problems. So looking at this first problem here, it looks like, if I can just glance at what's going on here, it looks like I have line A, which is bisecting, it's intersecting, how about that? It's intersecting KM. But what I just learned a minute ago is that if a point N is equidistant from the endpoints, then that means that it is on a perpendicular bisector. So again, these are equidistant, and then this is my perpendicular bisector. And what can I figure out? Well, how about what is KL? What is the length of KL? Units. In units. And how I can figure that out is, well, I've got two things that I can compare together now. If I know that Kn is equal to Nm, then if I write that as an equation, or I say, how about segment Kn is equal to segment Nm, and I do some substitution, I know that Kn is 14x minus 3, and I know that Nm is going to be 25, then I can go ahead and do some solutions here. So I'm going to add 3 to both sides, and then I have 14x, divide both sides by 14 to get rid of my coefficient, and x is going to be equal to 2. Well, now I can just go right back here and say, well, that KL is equal to 9x plus 5, and I know that x is equal to 2, so I would have 9 times 2 plus 5. So KL is 23 units long, and that's what we're working with, and we're trying to calculate. Now, if it was a perpendicular bisector, I know that this length is equal to this length. So I know that KL may be 23 units and LM is 23 units, and therefore I know that KM is going to be 46 units. So it's easy to work around a circle, a figure, a diagram, and start filling in what you know to make way and show you other things in the diagram. So here, looking at this one, we have line L, and it looks like it is a perpendicular bisector to segment AC. And, well, I should be able to look at this and say, well, if it's a perpendicular bisector, then this is going to be, segment AD is going to be equidistant, or D is going to be equidistant from A and C, so AD and CD are going to be congruent. So I also can see here that AB and BC are going to be the same, so AB is 9, and then I could go ahead and find out what this missing length is from DB using the Pythagorean theorem. And if we think about that, that would have been ABC, and it was A squared plus B squared equals C squared. And with that, I would say that, hey, this could be considered A, this can be considered B, and this could be considered C. And I could do those values there and figure it out. But just being able to identify that this is 16, this is 16, 9, and 9. I'm not going to go into the Pythagorean theorem right now. So just using some of our knowledge of lines and perpendicular indications and congruency, we're able to find out and construct those parallel and perpendicular lines, identify if they're parallel and perpendicular or skew lines. And I guess I should remember to add skew here. Remember, skew is neither parallel nor intersecting. So just keep in mind as we do this, we're always going back to these definitions. Always going back to the definitions. And I will just highlight that parallel lines have the same slope and they never intersect. And perpendicular lines have the opposite reciprocal slope. So if I multiply two lines together, if I multiply their slopes together and I get -1, then that is going to be perpendicular lines. Using the shortest distance theorem, the parallel postulate, and the perpendicular bisector theorem, we are able to find out a lot of information in our images and diagrams, and just being able to apply what we know and what might be considered practical knowledge in that construction of a parallel and perpendicular line, identifying parallel, perpendicular, and skew lines, and then solving problems involving the distance from the point on a perpendicular bisector to both endpoints on a line segment. Hey, it comes down to substitution, right? Make a little drawing, see what you got, and substitute the numbers and solve.